Okay, thank you. Good afternoon, everyone. Thanks for being here. And thanks AWI, Zach, and colleagues for keeping these workshop going on. Today I'm going to talk about challenges and opportunities for compound coastal hazards. And from the perspective of modeling and data analysis, especially when we're dealing with variable climate and factors that are going to affect flooding. A brief story, Hurricane Ian hit the coast of the United States late September, early October. It actually made landfall twice, both in Florida and Carolinas. And so if we look at the level of impacts, like thus far 148 deaths related to hurricanes have been reported, around 120 associated with flooding. Keep this number and this ratio of flood related in terms of hurricane death related. I'm going to use this number later. And of course, besides those, beyond those casualties, like roughly $67 billion in damage, made it a top 5 U.S. storm in the history of storms. However, those are sort of immediate impacts. If we look at the water quality and all the other factors affected by the hurricane impacts, those have been a disaster situation. Was it the only one? Of course not. Looking back into 2021, Hurricane Ida, 60 plus casualties, $75 billion of damage. So if you look at the history of United States in terms of climate-related disasters, only in 2021 there were 20 separate billion-dollar weather and climate disasters. The total cost $145 billion, which is the third most costly years on record after 2005 and 2017. And so if you look at the 2021 only, you will see multiple hurricanes hitting the coast of the United States. And if you look at the longer record of most expensive weather and climate disasters in the U.S., probably you see what I'm seeing here too, that over the past 20 years or so, there's been an increasing trend in the number of basically the costs associated with those weather and climate disasters. So we're dealing with those trending disasters. And so we need to better understand them and better get prepared for them. But looking into hurricanes, or generally speaking, tropical cyclones, what's happening during these events? Basically, a warmer ocean surface creates a low pressure atmosphere core on top of it, which has high moisture in it. This low pressure core creates a pressure gradient. So there will be high pressure outer, and there will be low pressure inside. Air is going to move towards the core of this, which we call it the eye of the hurricane. And this movement of air, we're in the northern hemisphere, so there will be a Coriolis effect that creates rotation around that core. That's what makes hurricanes. And these hurricanes moving towards the coast, they bring strong wind and, of course, a lot of moisture. This is the basis for two major drivers of flooding, because that wind is going to push ocean water towards the coast, which we call the storm surge. At the same time, that hot, low pressure, high moist air has great potential for torrential rainfall. So the combination of these two is something what we call the compound flooding. And so hurricanes, and generally speaking tropical cyclones, because these phenomena is called like cyclones or typhoons in the East Asia, the same concept, is causing a lot of damage and a lot of disastrous effect. So looking on Hurricane Ida back in 2021, which hit the coast of Louisiana, if you look at the record, down here you will see the record of coastal sea level, which you see there is a blue curve down here, which is the predicted tide, and the green curve down here is the observed coastal water level. The difference between that green and blue curve is what we call the storm surge. So you see there is a strong, relatively large storm surge mainly due to that strong wind which hits the coast. At the same time, if you look at the record of river flow at upstream, you will see roughly around the same time it experiences a larger peak flow rate at upstream. So basically people in that area are being affected from downstream by the coastal storm surge and from upstream from the river flow. These are the two phenomena that we might be prepared for each of them in isolation and separately, but not at the same time. Such coincidence or close succession of happening of those hazards is called compound events or compound hazards. Getting back to the basic definitions, IPCC, Intergovernmental Panel on Climate Change, defines compound events as two or more simultaneous or successive extreme events, or combination of extreme events with underlying conditions that amplify the impacts, or combination of events that are not themselves extreme but lead to an extreme event or impact when combined. So we now have the definition of compound events, but why do we care about them? Why do we need to analyze them more in depth? Because let me show you with a very simple example. Let's assume that coastal community which has a really well-designed drainage system that is going to keep them safe during a given rainfall with a given return period. That drainage system is going to be working and draining the runoff generated after that rainfall to the outlet, to the ocean outlet. But what happens if that extreme rainfall, which has been part of the design information, happens during a elevated coastal sea level, which the outlet is blocked? That means the drainage network is no longer capable to drain that runoff generated, and so leaves the community flooded. That's what we call it compound flooding, because that extreme rainfall happens at the time of extreme sea level. And so this is a very simple example. This is a schematic, but that's what we are actually experiencing all along the coast of the United States during tropical season. So what we can do, we need to first look at the design guidelines that we have with regard to characterization of hazard. Let's look at the hurricane scaling system that we are all familiar with. Whenever a hurricane hits the coast of the United States, the advisories are issued that this is a hurricane category 1, category 2, or tropical storm, and so on and so forth. We know that this scaling system is based on wind only. It's called Saffir-Simpson scale, which looks at the range of wind speed and categorizes them from 1 to 5. But if we look at the number of people died in the United States from tropical cyclones between 1963 and 2012, roughly 90% death occurred in water-related incidents, including the recent one that I brought up the numbers. So we're simply mischaracterizing the risk by focusing on the wind aspect of the hurricanes, while there are a number of casualties and damages and cost is associated with flooding. So this is one major issue that we need to consider, actually simplifying the events and reducing the dimensionality of those multidimensional events or multi-hazard situations into univariate basics. Our indexing system is not going to help us. It's simple, it's easy to communicate, but it's not comprehensive. It might cause misleading. So I'm going to give you one example of a research that we've done, and it's published in 2021. I had the pleasure to work with Dr. Moftakhari and one of his PhD students. So in that work, we have proposed a multivariate scaling system. And we said this is essential for characterization of tropical cyclones and going beyond the Saffir-Simpson scale system. The reason is that if you look at the record of historic tropical cyclones that hit the coast of the United States, and if you look at the combination of wind speed, which is a major driver of hazard, it causes damage. However, it's not the only one. As I said, it brings torrential rainfall, and that torrential rainfall is going to push ocean water towards the coast. Depending on where along the coast you are, it's going to push the water towards the coast and create a storm surge. So basically, we have three hazard drivers coinciding or happening in a close succession. If you look at the correlation structure between these three drivers, you will see that these are correlated. And so theoretically, I just explained that physically they are correlated and related. So now if you look at the relationship between these, and in this work, I promise I'm not going to show you any formulas or equations, but there are plenty of equations behind these. So the graph that you see here, we've developed based on joint probability concept based on using a couple of functions. The fact is that if you look at the joint probability of these events and categorize them based on the exceedance probability, you can generate hazard scenarios which are going to consider multiple drivers of flooding or multiple hazards at the same time. For example, you can call it a tropical storm or a Category 1 hurricane if the combination of wind, rainfall, and surge all would be a Category 1 event. Otherwise, you can have a relatively small wind coincide with a large flood event. Like Hurricane Harvey, the wind was not, when it made landfall, the wind was not that strong. But majority of effect was due to torrential rainfall, which the storm stopped over Houston area. So taking all those considerations into effect, we can come up with a multivariate index that can help us categorize. And if you look at those records, I'm not sure if you can see these names down here, but like looking at Saffir-Simpson scale system, 74 to 95 miles per hour wind speed is simply Category 1. And so if you look at Isaac, Sandy, Florence, these are Matthew, those are Category 1 events. But if you look at these multi-hazard scaling systems, those are all Category 2 to Category 3 events because the associated rainfall and the storm surge has been relatively strong and large. So this is a multi-hazard scaling system that we proposed and we validated against the reported damage. So if you look at the ranking of the damage reported for major hurricanes in the history of the United States, and if you look at the correlation between the scaling system based on Saffir-Simpson, which is wind-based only, and the scaling system that we proposed based on multi-hazard indexing, you see a significant increase in the correlation rate. And so you see from 0.59 to 0.78 correlation increases. That means, which is supported by the physics, we're showing that if you consider more physically relevant variables in your scaling system, of course you're going to get a better picture of the possibility of causing damage and the riskiness of those multi-compound events. So that was one of the examples of multi-hazard risk. But what we actually do in our lab, if you look at the classic classification of disciplines, we have a watershed hydrology that usually looks at the watershed processes. And we have a coastal oceanography, which looks at the oceanic processes, near coast and near shore processes, and so on and so forth. What we do and what we named our lab after is called coastal hydrology, which we are looking basically at the interaction between terrestrial flooding, terrestrial regimes, and coastal oceanic processes and their interactions in bays and estuaries and so on and so forth. The picture on the background that you see is the product of a research that one of my PhD students is doing on the coastal food, energy, water nexus. And in that paper, what we are doing, we're looking at how the classic and currently in use food, energy, water nexus concept developed in the hydrologic community falls short when comes near the coast, because at the coast we have sea level rise, we have salt intrusion, we have all other factors that are not the case inland. And so none of these factors have room in the classic watershed hydrology literature, and so food, energy, water nexus cannot be applicable. And this is going to be even more important if we see that, like at least in the United States, like 40% of the population live on the coastal counties, and a lot of business, a lot of production and consumption is going along the coast, and so those classic frameworks for the food, energy, water nexus are not going to be applicable. So that's one area of research that we are doing in our lab for food, energy, water nexus at the coast. But Getting further along into the concept of coastal hazards, I'm going to focus more on the flooding aspect of the hazards. And so what do we mean by compound flooding and what we can do in terms of opportunities? I talked about challenges and difficulties that we already have for classification and parameterization of those hazards. One area of research that we are exploring is exploring remote sensing and remote sense data to enhance the ongoing research on compound flooding. Back in 2018, we published a paper in Adjusting Emergent Hebraic Wetlands Elevation based with object-based image analysis and random forest. Basically, the whole idea here is that the most accurate the DEM digital elevation models that we have, which are the basis for any coastal flood modeling, is based on LiDARs. And those LiDARs, we know that they have some limitations when it arrives to vegetated area, because they're reflecting. If you see, once you see the schematic picture down here, you see that vegetation and the height of vegetation is going to affect the accuracy of those LiDARs. So in that paper, what we did, actually some of these papers have been led by my PhD student David Munoz, who is now an assistant professor at the Department of Civil Engineering at Virginia Tech. He left us last year to that position. And so on that paper, what we did, we looked at correcting those LiDAR data using random forest and based on the NLCD, National Land Cover Database. And so we came up with these differences, that there are some overestimation or underestimation of the elevation in a vegetated area that can be corrected with those machine learning algorithms. So this algorithm is available, and the tool for such correction is already available through our lab, and the paper already published. So if you're interested, please let me know. But the product of this the digital elevation model correction is going to be helpful for us to have a better understanding and better representation of a topography, which is going to be the basis for our flood modeling. Another application of the remotely sensed data in our lab is going to be, we developed a framework for using multi-source data to estimate the effect of urbanization, sea level rise, and hurricane impact on wetland change dynamics. Basically, the idea was that we have a relatively long record of remotely sensed data, like in areas like in Mobile Bay. And using those data, we can characterize vegetation and wetlands. And so what we can do using a well-trained machine learning algorithm, we can get back to the 1980s where those wetlands, like imageries, are available, and analyze how much wetlands we have lost or gained over time. So this is the outcome of that work. The blue curve at the top shows the trend in sea level observed at the outlet at the mouth of Mobile Bay, and the green and the red line show basically the trends in total wetland area and developed area. You see that we have an increasing trend in development, of course, urbanization happening around the Mobile Bay, and at the same time we're experiencing a decreasing trend in the total wetland area around Mobile Bay. And we know that those wetlands, beside their ecosystem benefits, they are like natural protections against coastal flooding for coastal communities. So these are another benefits of remotely sensed data, and fusing multi-source is going to help us to well characterize these patterns and trends. Another implication of remote sensing in our lab that we're exploring is flood inundation mapping. So basically, the extent of flooding has always been a question for post-flood analysis to know the extent of flood impact and looking what has been exposed to that flooding, the extent of damage and impacts. So the problem is that in many cases we have data scarce regions, which either we don't have in situ observations or gauges installed for a measurement, or if you look at the high water marks, they're happening a while after the flood, and or those areas might not be necessarily accessible. So gaining an accurate estimation of the extent of flooding has always been a useful information that we are always after. So in this work, what we did, we have combined multi-source remote sensing data. What did it mean? We have optical data which they are good when they're applicable. But we know that those optical information are not going to be useful when it's cloudy and when it's not enough light, like during night. We have radar data like SAR that are going to leverage, and work as a complementary source of data for optical information. And so even if it's cloudy or if it's night, those SAR data are going to work. So in this work, we have developed a multi-source, multi-temporal framework that combines optical and SAR data to have good coverage of flooding, and so somehow address the revisiting issues for relying on one source of data. If you look at this table, we use Sentinel-1, Sentinel-2, and Landsat-8. So Sentinel-1 is going to work as a radar-based remote sense data, and Landsat-8 and Sentinel-2 are going to be optical sources. And so once we combine them and use data fusion type analysis, we're going to come up with a multi-source multi-temporal flood extent maps generated. So these are the optical sources for Hurricane Harvey near Houston and Hurricane Ida near New Orleans. And these are the SAR data, each of which might have some gains and pros and cons. But when we combine them through a systematic framework, we're gonna capture the areas which is missing from each of those, and so the leveraging their skills is going to improve the accuracy. And this paper, we've just got the minor revision request yesterday, so it's gonna be out. It's with a IEEE journal that we're gonna submit the revisions soon. So I talked about remote sensing data and the benefits that they propose, but the problem is that remotely sensed data have issues of revisiting time. So we need to wait to we do not necessarily have good coverage at the time of peak of flooding, first. Second, there are some issues with calibration and validation, like thresholding, indexing, and coming up with like determining the depth of flooding, velocity of water at any given point. Those are not the products of satellite imageries or remotely sensed data. So what we are thinking is that we have another category of tools, which we call them numerical methods. We can simulate all those processes easily based on physics driven partial differential equations, but those numerical methods, they have their own limitations and the difficulties too, because we need to calibrate them and validate them. For validation, we need extensive data on that region, which is not necessarily the case. But if we combine them and link them and integrate them with those remotely sensed data, we can automate the process of calibration and validation. And so the skills can be combined to provide a good perspective towards compound flooding, which is itself a complicated process. So in this case, what we did, we looked at the Savannah Estuary at the border of South Carolina and Georgia for compound coastal flooding. And we developed a Delft 3D model for that area to consider the impact of compounding effects, because if you look at the guidelines, that's another issue that I'm going to bring it up. If you look at the guidelines for flood mapping in the United States, they are mainly based on univariate methods and univariate metrics. So we have a Bulletin 17B or Bulletin 17C, the latest revision, which is good for frequency analysis of inland flooding and riverine flooding. We have FEMA guidelines for coastal flood mapping, which are based on GEV, General Extreme Value Theory. But what about compounding? However, we have some guidelines that help us saying that taking the envelope of maximum from each of those, or for forcings, we have some FEMA guidelines that are going to give us a combination of riverine loads and coastal loads and so on and so forth. But there is no systematic way to combine them, and more importantly, those are not linear to be combined. So there are nonlinear interactions that needs to be considered, and those nonlinear interactions are not going to be in those linear equations of combining them. So what we propose here, we develop, and that's a very active area of research ongoing in the community for compound coastal flooding or coupled modeling. which means we couple hydrologic models with coastal models, coastal oceanographic models, or so-called ocean circulation models, to come up with the good boundary forcings of an area of the coast which is so-called freshwater influenced. So it's forced and pushed water from both sides, from downstream from storm surge and tides and upstream from the hydrologic regime. So in that case, in this paper we published in Water Resources Research, we showed how considering the compounding effect of drivers is going to deviate the estimates from the univariate metrics. And so what we did, we run that hydrodynamic model. We first calibrated and validated versus a few historic events. And then we showed that using the compound scenarios for flood modeling helps improve the accuracy of prediction of maximum velocity and maximum water depth. Of course, we're considering both drivers at the same time, and we're not simply ignoring one of them. The problem is that this might seem easy for all of us to see, okay, why do we easily do not plug both upstream and downstream? The question is that, let's say, if I'm going to design for a 100-year flood event, that's a typical return period that is used with FEMA for National Flood Insurance Program, right? So to delineate flood zone from others. So that 100-year inland would be a 100-year river flow, easy. So you would fit the Pearson type tree based on bulletin 17C, and you're going to get the design discharge. So you run your hydrodynamic model, that's easy. If you're near the coast, that would be a 100-year storm surge from GEV, and you're going to run your coastal model, you're going to get the flood extent. But when you're near the coast, these are interacting. So those are no longer independent. That means if you remember the basics of probability, probability of A and B is not simply of probability A times probability of B. It's going to be a joint probability concern here, which we need to resolve it. And that's why it makes it difficult. And those are the equations that I skipped here in this work. But we've shown that we can develop those joint probability concepts to look at the dependencies of these two and come up with a 100-year event. However, the problem is that there is no one 100-year event. There are multiple scenarios. Each of them would have the return period of 100 years. However, the strength of terrestrial versus coastal is going to be different. But so in this work, we've shown that there is a significant difference between maximum water level and velocity distribution if you run on the compound hazard scenario as compared to univariate scenarios. And that partially explains why we're lacking. If you look at the report that National Academies issued after the Hurricane Harvey, a majority of flooded areas in Houston were beyond the 100-year flood zone. Of course, one can negotiate that Harvey was not a 100-year event, but the question is that what is the return period of Harvey? Now, if you look at the literature, what was the return period of Sandy? There are tons of discussions around that. Depending on your perspective, whether if you're analyzing the return period of rainfall or return period of a storm surge or return period of river flow, you're going to get different numbers, of course. And if you look at the joint probabilities, you're going to get another different number. So this is an ongoing question, an open question. Was it a 100-year event? Probably not. But having like 70% of damages and flooded properties beyond the flood zone, is it acceptable? That's a question. That's an open question. So these are the things that we need to think about. Again, I'm opening up these lines of question. I'm not going to wrap it up in just 30 minutes or so. But these are the areas that we're exploring. That's another area, region that we are exploring. That's Mobile Bay. And so this is a Delft 3D model of Mobile Bay. And you see this is Mobile River, and this is downtown Mobile. You see this is the Mobile Bay and the Mobile River up here, and this is the downtown. And if you zoom in, with the help of those hydrodynamics models, we will be able to route the flooding throughout the downtown and elsewhere to come up with the flood inundation dynamics for flood management and flood estimation, depending on the forcings and forecasts. That's the one typical way that if you look at the estimates of like flood advisories or flood warnings issued around, Those are the typical type of analysis that they've done, but however, those are not at this detail. The reason is that they need to be practical and operational, so they need to lose some accuracy for making it fast. So the resolution might not be that high, and also many of those are based on, again, those univariate metrics that I mentioned earlier. Those are not necessarily coupled, and that's why one reason behind the recent findings that we've received through Cairo project for these like coupled modeling and like fast flood inundation mapping. There are multiple projects going on under Cairo, and one of those are, or basically two of those projects are the ones that I have the pleasure to work with some UA faculties. One of them is on machine learning algorithms for compound flood mapping, and the other one is nature-based solutions and how they prevent coastal flooding for coastal communities. And our study area is Mobile Bay for those projects. So there'll be more to come. But now the question is that we know the benefits of remote sensing. We know the benefits of numerical methods. We know the benefits of statistical methods. But if you look at the literature, these methods are applied individually and in isolation and separately. So we have thorough analysis of statistics of flooding here and there, not necessarily mixed with numerical methods. We have thorough analysis of extent of flooding from satellite imageries and satellite products, not necessarily verified and compared to numerical methods, not necessarily looking deep at the statistics and joint probabilities. So I'm giving you one example. If you look at the databases already published by Army Corps, there are synthetic tropical cyclone storms. Those are the storms that have been generated based on the historic records that can be potentially hitting the coast of the United States, and those synthetic storms are used for design purposes and many other flood impact assessments. If you look at them, there are thousands of them. And if you have been any time along your career been dealing with those numerical models, you know that how computationally expensive it is to run all those thousands of simulations, even with the help of powerful computers that are available these days. So now the question is that, do we really need to run all those thousands of simulations to get the extent or the range of possibilities for extreme flooding at a given point? For example, if you're a flood manager in Miami or, I don't know, Houston, do you really need to run all those thousands of scenarios on your computationally expensive? Because look at the area and so the mesh, and if you're going to make it fine enough in terms of a couple of meters in urban areas, that's going to take a really long while to run all those scenarios. So do we really need to run all those scenarios to get the extent of flooding? We guess that it might not be necessarily needed if you have a specific objective. For example, if my intention would be to focus on compound flooding in Houston area or Galveston Bay. Galveston Bay would have storm surge coming from the Gulf of Mexico, and it has a given watershed. That if I would be able to look at the correlation and dependencies of the wind offshore that is going to push the water towards Galveston Bay, and if I look at the dependency of rainfall over that entire watershed with the flux of fresh water to Galveston Bay, the upstream boundary condition of that system, if I know how these drivers are going to be correlated to the upstream and downstream boundary conditions that are going to derive compound flooding in Houston area, I might not need necessarily to run all those scenarios, because one of them might go this way and might not create much of flooding in Houston. However, some of them might cause severe flooding. To look at this, what we developed a concept called cumulative likelihood of impact. In that sense, we look at those thousands of scenarios of path of hurricane and look at their path along these squares. Each of these squares, the darker one, has the largest correlation with the storm surge created at at the mouth of Galveston Bay. So you see that if the strong wind passes through these pixels, is going to create a larger surge down here in Galveston Bay. But if it goes far from here through these pixels, it's not going to create much of a storm surge. That means if I run hundreds of scenarios that pass through these pixels, I'm not going to get much of flooding. But if I focus on those 3, 4, 5 that are going to go through these pixels, I'm going to be probably getting the most extreme flooding that has potential to affect the Houston area. That's the whole idea behind this. And the beauty of this method that we're about to submit to the journal is that it not only considers the correlation of offshore wind and the storm surge, but also it looks at the correlation of inland rainfall and river flows. So both upstream and downstream, the compound flooding is going to be there. And so under that cumulative likelihood of impact indexing, we will be able to rank those scenarios. And so to demonstrate the application of this method, what we did, we look at 13 historic events in the history of Galveston Bay that basically hit coast of Texas, and so since 2008. And so if you look at the events, of course, Harvey and Ike are going to be the larger events in the history. And what we did, we basically first started ranking based on our index. So based on our ranking of cumulative likelihood of impact, Harvey, Ike, and Bill and Edmond. So these are the rankings that are coming from out of our cumulative likelihood of impact indexing system. Now, if you look at the observed water level, so each of these charts are going to show the observed water level at given gauges A, B, C, D that you see on this map all around the Galveston Bay. So if the longer pie for each chart would have the darker color, that's a proof that this cumulative likelihood of impact is going to work, because the darker color is going to be associated with larger index value. And the longer pie is going to be the depth of water in that gauge. So if we look at gauge C, for example, you see that the top 3, the longest pies down here are going to have the darkest colors among all. The same here, more or less the same here, depending on where the gauge is located and where was the pass of Harvey and Ike. So it roughly demonstrates that once you get, if you would have to filter out 10 storms out of 13 that you already have in the history of Houston to simulate in your numerical model, even before observing the impacts, our cumulative likelihood of impact, it tells you if you model these 3, you're going to get the most extent of flooding without needing to run the other 10. So the same would be applicable to those thousands. So you can come up with like 30, 40 select scenarios. That's kind of dimensionality reduction. So you can come up with 30, 40 type of scenarios of hurricane and simulate them in your numerical model and come up with the results which you are hopeful to get the extent of impacts among those thousands of scenarios. That would be the next step up in our research. Once we get it published, we're going to go through those thousands of scenarios, and we're going to work. We have another work with the AirDeck, Army Corps lab in Mississippi, that through them we would be able to get the simulation of those thousands of scenarios, and then using these indexing systems to see whether if this indexing system is going to work at that large scale as well as not. So that's the next step. Tune in for results. Another area, I'm about to finish. I have 2 to 3 more slides. Another area of research that we were working on is that, let's say we have powerful numerical models, and as I just mentioned, running those for larger areas for fine resolution is going to be computationally expensive and not practical. So what we can do, and we have statistical models, that those statistical models are bounded by the availability of data. So you cannot well train a a statistical model or machine learning algorithm where you don't have much of data. Well, because the process of training needs a lot of data to train. So what we do, what we propose in that paper is that why don't we focus on one portion of the coast which has ambient observational data, and why don't we well train a machine learning algorithm and let it go along the larger coast? So that's what we call it, from local to regional compound flood mapping, with the help of course, deep learning and data fusion techniques. In that paper, what we did, we looked at the path of a hurricane Matthew, and so what we did, we trained a machine learning algorithm, a deep learning algorithm for the Savannah estuary at the border of South Carolina and Georgia. And so what we did, we let that data fusion algorithm to go along the coast and creates flood maps for the entire coast, which hasn't been seen before. It was just that model has been trained for this smaller portion of the coast, which is located somewhere here, but is able to provide flood maps for the entire coast. And so we have validated this work, and the results are already out there. It's published last year. So if you're interested, please look at the results. The results are pretty promising and interesting. So that's one benefit of training a deep learning algorithm. And of course, data fusion needed, so because we used satellite imageries and combined satellite imageries and numerical methods to get a better result, and so for the training process. And based on those satellite products, we were able to map the flooding over the entire coast. And I guess this is a different paper. This I misplaced it here. This is another paper that we did. No, that's a correct paper. Sorry, my bad. So this shows the flow of the activities. So at the local scale, we collect satellite, radar, lidar, and DEM inputs, and we plug them into the convolutional neural networks and data fusion framework. However, it is also receives the input from hydrodynamics models, because those hydrodynamics models are going to be providing a lot of information about the extent of flooding and flooding characteristics. And so once we get it trained, we do through some thorough model training and validation, and the pre-trained model weights are going to be going through a transfer learning process. And this transfer learning process is going to enable us to apply this methodology into a larger area. And these are the products for validation at the regional scale. And again, so I encourage you to look at it. The last study that I'm going to highlight here is we have difficulties with this data scarce areas, because, and that's part of our responsibility as scientists, to help those people and those communities to get better informed. So the problem is that if you look at, for example, we do have, if you look at the most recent publications out there about the sea level rise and coastal flooding and so on and so forth, majority of them are based on the information collected at gauges. We have very good information, a good understanding about the dynamics of flooding at gauged areas, but for ungauged areas, we don't have much of an understanding. I'm bringing an example of high tide flooding, also called nuisance flooding or minor flooding. High tide flooding is a phenomenon that happens over high tide periods. It's a type of flooding. It's a kind of minor flooding. We call it minor because it doesn't cause damage or structural failure or death or injuries. But it's just a few inches of water on the ground, makes socks wet and closes businesses, interrupts traffic, right? So you might, at the incident level, you might not care about it much, because you might see, okay, so why should I care? It comes and goes away. But the problem is that those business closure and traffic interruptions and health impacts and so on and so forth, when accumulated over time, are going to be significant because those extreme events that we are worried about are going to happen once in 100 years. That's why we call them 100-year event. However, not exactly once in 100 years, but on average, we expect them that theoretically happen once in 100 years. But those high tide flooding events are going to happen on a very regular basis, or even a weekly basis, multiple times throughout the month. Look at like Maryland, Florida, many of those east coastal states are experiencing these. And so if the accumulation of the costs associated with this, the business closure for a few hours during rush time or traffic interruptions, if accumulated over time, is going to be some significant over time if you accumulate it over like 20 to 30 years. So now the question is that the thresholding of those high tide flooding and assessing the dynamics of it is fairly dependent on the local tide data available. We have pretty much like, and that long record of tidal observation is a key to be able to characterize these. The problem is that, like, if you look at along the Gulf Coast of the United States, there are like less than 10 long-term observational gauges for tides that we can rely on for developing a high tide flooding threshold and the dynamics for the future and sea level rise projection and so forth. That's the motivation behind our very recent study. What we did, we looked at the historic record of those gauges, and we looked at the geographical features, geophysical features that are going to be drivers of sea level rise and high tide flooding or nuisance flooding. So using that, we are training a machine learning algorithm. Here we're using random forest to develop same thresholds and sea level rise rates for the points that we don't have observation. That's why we have the product right now. We got it just a few days ago. It's a spatially distributed sea level rise rates. That's something that is not available out there. And so this is a very novel product. This is going to really help us because if you look at the gauges, that's one of them here, one in Tampa Bay, goes back to Florida Panhandle, maybe something around New Orleans, and then, so what about in between? We have no idea. What about the communities in between? What would be the threshold? What would be the information that they can act upon? Those are not available. That's what we're doing. So we are creating a spatially distributed sea level rise rates along the CONUS, entire coast of East and Gulf and West Coast of the United States. And we're also training another machine learning algorithm to give us the spatially distributed threshold for flooding. Because those flooding thresholds are also very gauge oriented. If basically you have minor flooding threshold for Miami, and that's based on a gauge near Miami. So what about in between all the way to Orlando or back all here to the coast of Georgia? Those are the things that we do not have it available. And those thresholding system, not only for coastal, it's also important for inland, but we are focusing right now on the coastal flooding thresholding. And at the moment, we are focusing on high tide or minor flooding. Well, we are planning to go and move and to make it thresholding for moderate to major flooding as well. And I would like to thank, what I presented today was not my own work. That was a group of scientists. I had the pleasure to work with folks at Center for Complex Hydrosystems Research and other faculties at UA Civil Engineering and the PhD students. So I'm just presenting here. That's not my own work. And of course, I would like to thank the funding sources who made those research possible. Here are my contact information. If you have any question or you see any room for collaboration, please shoot me an email. I'll be happy to discuss this with you. Thank you.